Hello, everybody. Thank you for coming out so early on Wednesday morning after a night out. My name is Tom Adamski. I'm a principal solution architect. I'm joined today by Ankit, also a principal solution architect. Together, we have more than 10 years of experience working with customers, setting up their networks and helping them with network security. And the session we have for you today is around firewalls and when to use them, and maybe when not to use them. So we're going to ask ourselves when to firewall, when not to firewall. And then we will look at different use cases where we typically would use firewalls and see if we have some alternatives that might make it easier for you to achieve the same level of security, but make it simpler from an operational point of view or optimize for cost. Every once in a while, we'll pop these pink rectangles that will give you tips or show you what's important about each slide. So I want to start off with different connectivity models that some of which you might already be familiar with, some of which might be new. So we have two different network connectivity types, the traditional network-to-network connectivity, and then the other one is application networking. So we'll use an example, and you'll see that there will be a lot of examples throughout the session. We barely use any text. It's mostly diagrams. On the left-hand side, we have client VPCs with some client, and on the right-hand side, we have our application VPCs with a couple of applications. There's a HTTP application and some database, and the goal here is to get the client access to those resources. With traditional networking, what you would do is you would create some logical network pipe between those VPCs, and then set up routing in both directions to allow traffic to flow. But with that, you're allowing the client VPC to talk to anything in the application VPC. You're also allowing the application VPC to initiate connections to anything in the client VPC. So you would typically start adding additional restrictions, so security groups, which are always there that you have to configure, to limit access of what the client can get to. And then very often, you would also look at adding some additional firewalling constructs. So either use an AWS managed next generation firewall or bring a third-party appliance firewall to put in place. On the application networking, we're looking at a slightly different model. With application networking, what we're doing is we're making it look as if the application or database you're trying to get to is actually hosted inside of the client VPC. So it will be exposed as an IP address, a port, and you will expose individual application one by one. And then client can connect to those applications. With that model, you're already getting a certain level of access control, right? You're not opening up the networks. You're only allowing the specific resources between the client and the application. We're also allowing for overlapping address space in this scenario, so you don't really have to care about routing and IP addresses. It makes that model a little bit more simpler. If we overlay some of the services that facilitate each type of those, the connectivity model, for network-to-network connectivity, there will be constructs like the Transit Gateway or Cloud One, which are kind of distributed routing services inside AWS, or VPC peering, which is probably the simplest one, which actually looks like that pipe that I showed you. For application networking, we're going to look at Amazon VPC Lattice, as well as AWS Private Link. Now, our session is going to kind of straddle the line between both of those connectivity models. But if you do want to have a deep dive on each one of those models, some of those sessions already happened. One of those sessions is actually happening next door to us. But I'll see if you start switching your headsets to the green color, so stay on blue. So our question today is going to be to firewall or not to firewall. And we're not saying not to firewall in terms of don't apply security policies. I actually personally really like firewalls. My best friends are firewalls. But what we're saying is firewall when you need to, but look at alternatives if they give you more flexibility or make it easier for you to deploy things. When we're looking at firewalling solutions today, we're going to talk about AWS Network Firewall and then Web Application Firewall. Both are AWS managed firewalling solutions that will scale alongside with your load, so you don't have to deal with patches, updates, scaling. That's all managed. But then there are differences between them. So Network Firewall operates at layer 3 all the way to layer 7, but it's focusing on TCP and UDP applications. So pretty much any application, any port. It can also cover HTTP, HTTPS, But typically, if you have a use case where you're allowing traffic from the outside to your resources, you want to be using a web application firewall. That's purposely designed for HTTPS applications, comes with a lot of bells and whistles, specializing in protecting your web application, all the way to advanced things like bot detection and account takeover prevention. Another difference between those two firewall types is that network firewall, you use routing to navigate traffic to network firewall. So you have to be operationally moving the traffic towards the direction of the firewall to get it inspected. With web application firewall, with WAF, it natively integrates with a lot of AWS services, so CloudFront, API gateway, application load balancer. So what I want to start with is give you a reference architecture for how your network would look like if you did firewalling everywhere. And by firewalling, I mean add additional third-party firewalls, right? Or AWS managed firewalls. You still would do security groups and all the other services, but we'll look at those additional firewalls here. And we'll look at different use cases, and you see there's a legend there. Different flows will have different colors, and we'll start with the ingress flow. So ingress is where we have an application that's internet-facing, and we have users out on the internet that need to connect to that application. So we would have an application load balancer, maybe make it public-facing, and then deploy web application firewall on top of that application load balancer, and that might be it. Maybe we're done, and we have now protections for users coming to our applications. However, typically with web applications, you would also care about experience. You might want to do caching, so you would often put your web application behind a content delivery network. AWS has Amazon CloudFront, which is a content delivery network that also integrates with AWS WAF. It's a single button integration on a single API call. So now your users would be hitting CloudFront closest to where they are. They would get content from cache, they would get inspected before traffic gets forwarded to our application. Some of the cool features that CloudFront actually launched recently, they allow you to also connect to an application load balancer that's private. So you could completely hide your application, your origin, from facing the internet and have all traffic coming in through CloudFront before it gets to your application. And then as you add different applications, you would horizontally scale that environment, add additional VPCs, and each one would be fronted by CloudFront. We call this model distributed ingress. So every VPC has its own load balancer, and it has its own access from CloudFront. Sometimes customers would want to centralize that ingress. It's not exactly a best practice. Sometimes you just have to do it, and it's fine. But we tend to recommend distributed ingress. So have different VPCs, each one with its own path. That's the most scalable, and that's the more cost-effective model for ingress. Now, if you want communication between those VPCs, right, maybe we have hundreds of those VPCs. I'm only showing you two. We can connect those to routing constructs inside of AWS region. Could be a transit gateway, could be AWS Cloud One. And then we would deploy a VPC called the inspection VPC with maybe AWS Network Firewall. By the way, we just launched a native integration between Network Firewall and transit gateway. So you wouldn't even have to build this VPC to be able to solve this use case. So once we have the firewall, we will navigate traffic through transit gateway or Cloud One, push it to the firewall stack, inspect, and then send it to the other VPC. We'll actually show you a more detailed design on how actually we need to do it with routing and what are the routing tables and routes in each layer. Finally, for egress use case, we could use the same VPC. We could put a NAT gateway in there. And then egress traffic, so traffic that originates from an EC2 instance or pod or a container, would be sent to the transit gateway or Cloud One and then sent out through inspection VPC. So you'll notice for egress, we actually do recommend centralized egress. That is actually the more cost-efficient model and allows you to scale better and be more efficient at using your resources. Right? You deploy the NAT gateway and the firewall, and you can have multiple VPCs share that layer. The other interesting thing I want to call out here is that we now have a different path for traffic coming in from the internet. It hits your workloads, and they respond back to the load balancer, then go out back through CloudFront. But then if an instance on your workload initiates a connection, it will send traffic to the transit gateway and then use that centralized egress for getting out. Okay. So if we zoom in at each firewall layer and kind of understand what do we see customers do at this layer. So with AWS WAF for ingress, typically what customers do, they can set up IP addresses and port-based rules, but they often do things like geo-blocking, they add rate limiting, bot control, and a lot of different rules protecting against the OWASP top 10 risk, so SQL injection, cross-site scripting, what have you. For egress use case, what we see customers deploy on the network firewall is often would be domain filtering. So you want to limit the domains that you allow your clients to connect to. We also support geo-blocking, so you can limit the countries that you're connecting to. There would be some protocol enforcement, so validating if that HTTP request that I'm doing is really HTTPS and not some other protocol pretending to be something else. Traditional IP port-based filtering, JAR 3 and 4 fingerprinting. So this is super relevant if you don't plan to decrypt traffic. You can actually fingerprint the client and the destination and make sure that you're allowing traffic to the legitimate destinations, even if the traffic is encrypted. And then finally, optionally, you can do TLS decryption if that's something that you need to do. So network firewall supports that. For the east-west use case, so VPC to VPC, what firewalls typically do is a lot of it would be IP port-based rules. So your VPC would be a security boundary, and then you would set that up inside of the firewall. Maybe the central security team is controlling access between different VPCs, subnets in that VPCs. There will also be some protocol enforcement as well as domain filtering, so validating the domains you're connecting to. Now for completeness, there are also use cases for connecting back to on-premise. Right, so maybe you have a corporate data center, you might have a direct connect, which is pretty much fiber to our backbone, or use an IPsec VPN. And that traffic can also hit the transit gateway or Cloud One, and you can push it up to inspection. So this use case is pretty much the same as the east-west use case. The direct connect or VPN is just another attachment on the transit gateway or Cloud One. And the same thing goes for remote user access. So maybe you have users at home that are connecting using AWS Managed Client VPN. The traffic would be brought into a VPC, and then from that VPC, they can get to all the resources. And again, you can push that traffic up to inspection, to the inspection VPC, to apply your policies. So we talked about our firewalls, but there's also a lot of other security services that I'm not going to mention in the session. We have DNS firewall, where we can filter your DNS queries at the DNS level rather than before even traffic gets sent on the data plane to the final destination. We have our network access control lists and security groups, which are always there and available for you for free inside of the VPC. We have Firewall Manager for managing all of these different constructs, including the firewalls that we talked about, sent from a central account. Shield for DDoS protection, and maybe guard duty for threat detection inside a VPC. So there's a lot of things that you could be deploying inside of the VPC to secure it. But today we're purely focusing on the next generation firewalls, or web application firewalls. Okay, so let's look at the different use cases now one by one and talk about, is this the best practice? Is this what we would recommend? Or is there an alternative that you can look at to make your life easier? So we'll go back to our reference architecture, and we'll just focus on the internet ingress use case. So clients connecting to the workloads through CloudFront and application load balancer. And the good news here is, yes, this is the best practice. Right? If you have a web application firewall is what you want to do. Now, but that is for web applications. What if you have applications that are not HTTPS? Right? What if you have TCP, UDP applications? Maybe you put them behind the network load balancer, or maybe they're directly facing the internet. What do you do with that traffic? So one option is to deploy security groups on the network load balancer. However, security groups have a limit of how many rules you can configure, and that number is 1,000. So if you need more than 1,000 entries, security groups are not going to be sufficient to limit access to your resources. So you can also use network firewall. And this is also a recent launch. So typically, prior to this launch, you would have to put the full-blown network firewall inside of that application VPC in front of your network load balancer, and then configure routing to make sure traffic is forwarded correctly. With the recent launch, you can have the network firewall in a different VPC, and create a logical endpoint that can navigate traffic to that centralized firewall. So the endpoint, think about it as an extension, a long arm of that firewall inside of your application VPC. So you still have to set up routing, so that's still always there. So you need to make sure that as traffic is coming in, you're forwarding it to the network firewall. But then from there, the network firewall endpoint will pass it on to network firewall. Network firewall will apply your policy, decide if traffic is allowed, and then it can continue to the NLB. But then the question here would be, what is your non-web application? And then the reason I'm asking that is there are a lot of AWS managed services that can replace some of the pain points that you have with having to manage some of these applications. So if your use case was exposing an EC2 instance and providing SSH access, we actually do have a couple of managed services that can allow for you to have this managed access through the browser or directly through the CLI, where we manage the SSH keys for you, and you can use identity and access management to provide access. For use cases like FTP, SFTP, we do have AWS Transfer Family, which is a managed service that can solve that use case for you. And finally, if you have emails, we have a simple email service as well. So we can look at an example of accessing an instance over SSH. Right, so if we use Systems Manager, Session Manager, our EC2 instance will do an outbound connection to the Session Manager service that lives in the same region. So notice, because this is an outbound connection, you don't have to open any inbound rules. So your security groups could completely be locked down on the inbound side, or you can have a firewall blocking all the traffic in. But as long as the instance can call out to the Session Manager service, then the users would talk to the Session Manager service, and Session Manager would stitch those two sessions together to allow you SSH access to your instance. You don't have to set up any inbound rules. You don't even have to have a firewall in front of that. Moving on to internet egress. So let's go back to our reference architecture again and pull on the internet egress use case. We'll show you what the life of a packet looks like in the internet egress flow. So let's imagine our instance is trying to get to GitHub to pull some code or do a software update. The first thing it would do is it would do a DNS lookup. So if you enabled Route 53 DNS resolver firewall, you could actually validate if the domain they're looking up is legitimate, or if it's a domain you want to allow that traffic to. Say you want to allow it, GitHub is fine. The next thing you need to make sure you configure is routing inside that VPC to forward any internet-bound traffic to Transit Gateway or Cloud One. On Cloud One or Transit Gateway, you would also need to make sure you have routes forwarding the traffic, outbound traffic, to the inspection VPC. And then I simplified this drawing quite heavily. The inspection VPC, inside of that inspection VPC, each component actually lives in a different subnet and will have a different route table associated with it. Because what we want to do is, as your traffic arrives in the inspection VPC, we want to bump it into the network firewall, do our inspection on network firewall, but after that, bump it into the NAT gateway. And after NAT gateway, once we NATed the traffic, send it out to the internet. The good news here is the firewall can actually see the original IP address of the client as well as the destination. So you can apply your policy just like you would with on-premise. One side call out here is if you have an IPv6 use case, you would actually have to put proxies inside of that egress VPC, or do not do centralized egress. If you want to have more questions on that one, we can chat afterwards, but just be aware that V6 is a slightly different use case here. So good news also is that doing network firewall for egress is also the best practice. It's a really good solution for that use case. But what I often see customers do that's kind of a problem, they use the same path for connecting to AWS managed services. So inside of the region, we might have hundreds of AWS managed services. I'm showing you only three. S3, which is a storage service, DynamoDB, a NoSQL database. And then as an example of all the other services, Elastic Container Registry, ECR. This is where we manage container images for you, so you can upload container images there or pull container images from there. The reason why I'm showing those is usually those three are generating a lot of traffic. And then pushing a lot of traffic through Transit Gateway, NAT Gateway, Network Firewall adds latency. You can inspect that traffic, it will work, but you'll pay more money and you will add latency. So the best practice to talk to AWS-based services is to not use your egress stack, but instead use endpoints. So S3 and DynamoDB have two special types of endpoints. They're unique in that aspect. They have gateway endpoints. I like to think about those as wormholes to your VPC. Right? And to get traffic out through that wormhole to the service, you need to make sure you update your routing tables and say that S3 prefixes should go to the S3 gateway wormhole, and then DynamoDB prefixes should go to DynamoDB gateway. And you don't have to manage those prefixes. You don't even need to know what they are. We have a managed prefix list for you that represents all of the S3 ranges or all of the DynamoDB ranges that you can use. What about all the other services that don't support gateway endpoints? So for those, you would create interface endpoints. There's no routing required. With interface endpoints, that's one of the application networking constructs. Interface endpoints are presented locally inside of your VPC as an IP address. And we will update DNS under the hood to redirect your traffic to ECR to go and talk to the endpoint instead of flow through your egress stack. Now, but you can ask, what about security? How do I make sure no one connects to a bucket that's not my corporate bucket, or no one connects and downloads an image from somebody else's image repository? Well, you can apply policies on the endpoints to control data access. Who are you talking to? What destinations you can communicate with through these endpoints? So in this scenario, in this example, we're setting up a policy on the interface endpoint to say that we're only allowing to download images from a specific AWS account. And if I try and download a random image from somebody else, that's not going to be allowed. I'm also making sure that the requests are coming from a particular org. And this is separate to the policies that you would be setting up on the resources themselves, right? On the S3 bucket or on ECR itself. This is purely a policy on the endpoint to control what can you allow to get out. Okay. There's another use case I want to touch on that we haven't really mentioned earlier, internet air-gapped workloads. So this is not really egress or ingress. This is where you want to deny both of those use cases. So you might have a workload that you don't want that workload to talk to the internet. So what would you do? What can you do to limit access completely from the internet? So cut off that workload. Well, you could think you could do network firewall and endpoints and block that traffic. That will technically work, but it's unnecessarily complicated for that specific use case. So the other options, the other things that customers would do is they would remove an internet gateway from a VPC. That's one option. If the VPC doesn't have an internet gateway, it's not talking to the internet. The other option would be to use network access control lists or security groups to limit that access. So that's still valid. But something that we launched earlier this year is your ability to block public access to your VPC, and we called it VPC block public access. So with VPC block public access, you can centrally manage and declare access controls for a set of VPCs. So you can do that on the account level, OU, or across all of the organization. Basically, you would say, I don't want any VPC in my organization or any VPC in an account or in an OU to have any access to the internet. And you have the ability to exclude different elements. So you want to exclude an account. You apply the policy on an OU level, but you want to exclude an account. Or you apply the policy on an account level, but you want to exclude a VPC or a subnet. That's totally possible. And then you can decide if you want to apply blocking on just in both directions or block only inbound traffic and still allow the outbound traffic. And that still applies on VPC subnet account level. So the beauty of that is this is independent from what anybody else configures inside of that VPC. So even if I mess up configuration of the VPC and I have an internet gateway, I opened up my security group, I messed up the knuckles, normally traffic would just flood into my VPC. If someone enabled block public access at a central level, so usually a central security team, nobody can get into and out of that VPC. And then finally, you can use a network access analyzer before you enable this feature just to validate what would be the impact, right? You want to check before you block public access to all of your VPCs. Okay, so with that, I want to move on to workload-to-workload communication and hand off to Ankit to continue.
Thanks, Tom. So folks, in this next section, we are going to be talking about workload-to-workload traffic patterns, inspection architectures, and any alternatives. So firstly, let's look at a workload-to-workload inspection-based architecture. Your use case is two VPCs. The VPCs can have various flavors of computes inside of them. They are connected to each other using transit gateway or cloud WAN. And your use case is to punt all the traffic between these two VPCs through an inspection firewall that is also connected to the transit gateway. Now, earlier you heard Tom mention that you can use routing tables to influence traffic between VPCs. So in this case, you would have a static route within your source VPC that would punt traffic towards transit gateway or cloud WAN. Now on the cloud WAN or transit gateway, you would need a route that sends traffic to the inspection VPC. Within the inspection VPC, you would have a route that would send traffic to the firewall endpoint. Firewall does its firewalling, and then you're going to need a similar routes for the return traffic as well. Now to send traffic towards the destination VPC, this is where you could use propagated routes on cloud WAN or transit gateway, and traffic gets sent to the destination VPC, and the reverse direction as well. Now a pro tip here is you should use appliance mode on the inspection VPC attachment for multi-AZ scenarios. That would keep your traffic symmetric. So talking about firewalling, let's actually take a look at what the firewall does most often. So you could insert a firewall between two VPCs, which we saw on the previous slide, which basically gives you VPC one-sider to VPC two-sider kind of a policy. Alternatively, you can insert a firewall endpoint or a firewall between two subnets of the same VPC. For example, between two subnets of a shared VPC. Now, ultimately, the policy that we see customers deploy for east-west inspection or for VPC to VPC inspection follows the 5-tuple construct. So basically, it's source IP, destination IP, source port, destination port, and protocol. Now, since this is mostly based on siders, it really sounds like access control versus deep packet inspection. So with that, let's see if there is an easier, more cloud-native way of performing access control between your workloads. This is where we'll start talking about VPC Lattice. So VPC Lattice is a fully managed service that allows you to securely connect your workloads, and you get additional observability-related benefits as well by looking at VPC Lattice access logs. Now let's define the use case again. You have two VPCs, and your use case is to provide access control when workloads within these VPCs talk to each other. So this time you would have a VPC Lattice service network in the middle. Your VPC Lattice service network is an aggregation point or a logical grouping of your services or your applications that require similar connectivity and security. So the first point to remember with VPC Lattice is you onboard specific applications onto VPC Lattice. So from here on, I would use the words applications and services interchangeably. So the first step you take here is you create this service called Service 1 on VPC Lattice, and you say that, okay, this Service 1 has a backend target or a target group that is EKS in the EKS cluster in your app VPC 1. So from this perspective, your VPC Lattice feels a lot like a load balancer in that you're onboarding an application and you're providing a backend target group as well. Now, optionally, when you onboard a service, you can provide custom FQDNs or vanity domain names as well. Once your application is on Lattice, there's got to be a consumer. Somebody must want to access it. So this is where you create a service network VPC association. Now, major point to remember here is when we say VPC association, it means workloads only within that VPC get access to that service. So let's look at the life of a packet or the traffic flow. The instances in app VPC 2, when they want to consume this service, they would want to access an FQDN. They try to resolve that. That FQDN resolves to an IP address that puts traffic onto the VPC Lattice data plane. Another thing to remember here is this IP address is only available from within the VPC. It's non-routable. Once traffic is on the VPC Lattice data plane, this is where Lattice understands that this traffic is destined to Service 1, and Service 1 lives in the EKS cluster behind app VPC 1. So from this perspective, your Lattice acts as a combination of your load balancer that allows you to onboard specific apps with a target group and also connect your consumers with service producers. Now let's talk about security. You can optionally provide VPC lattice auth policies as well, and you can apply these at two separate levels. Firstly, you can apply the auth policy at the central service network level. This is where you could apply a very coarse-grained policy. For example, saying that allow this request as long as the originator of this request was within my AWS org. Now, pro tip here is, since it's applied on the central service network level, it'll be your central network or security admin team that would create and apply this policy. Okay, so the policy or the user request is now approved or allowed at the service network level. The second place where you could apply a policy is at the actual service level as well. And this is where you could get really granular with your policy. So in this case, I'm saying, allow the request only if it comes from a specific AWS principal or a role. And at the same time, when it's going to only a very specific resource, which is a service within Lattice. And when the principal is making a get method request versus something else. So it allows you to get really, really granular at the service level. Now, often enough, it's going to be the actual application or service owners that would have intimate knowledge of how their service should be consumed by the consumers. So this auth policy on the service level would likely be applied by your specific app owner accounts. Now, another pro tip here is use SIG v4 signed request for creating really granular auth policies, for example, matching on your principal IDs. I'll take a sec here in case you want to take a photo. All right. All right. So let's expand your use case. So earlier we saw how you had one service. Let's say another application team wants to onboard their service onto Lattice. So you onboard that service, service 2, onto VPC Lattice Service Network. From a data path perspective, everything remains the same. Your instances or your consumers want to access service 2 this time. So they open a TCP connection to port 443. Once traffic gets sent onto the VPC Lattice data plane, Lattice understands where this traffic must be sent. So instead of service 1, this time it's sent to service 2 towards the ECS cluster that's in app VPC 3. So again, the net takeaway here is for your HTTP, HTTPS services, Lattice can act as both a load balancer and a router at the same time. There is another mode in which you can use VPC Lattice, which is for TLS pass-through. So often customers want to use mutual TLS between client and the actual destination. So the good news with Lattice is Lattice doesn't break or terminate the connection in the middle. So when you use TLS pass-through with Lattice, the TLS session is terminated directly between the source and the destination, which gives you true end-to-end mutual TLS. So now we spoke about your HTTP, HTTPS applications and TLS pass-through. That opens up the question of what happens when you have a non-web app. For example, a native TCP application like a database. So Lattice supports that connectivity as well. For that, you need a new Lattice construct called Resource Gateway. When I say new, it was launched reInvent of last year. So a Resource Gateway is your entry point inside of a VPC. To onboard a TCP resource, you first need to define the resource. In a resource config, so I say that, okay, this specific database inside of my VPC is my resource. Then you associate the resource config with the resource gateway, and then finally you put that onto the service network. So net-net what you get is, in addition to your HTTPS services, a TCP resource as well that is listening on a specific port, port 5432 in this example. For TCP resources also, you can optionally provide a vanity or a custom FQDN. Now, let's look at the traffic flow in this case again. Your instances, they send their DNS queries. With the response, the traffic gets sent onto the VPC Lattice data plane. Now again, since Lattice knows where this traffic must go to, this traffic is sent all the way to the resource gateway that lives in app VPC 3. A key point to remember here is your resource gateway gets IP address from the VPC where it's created, And when the resource gateway sends traffic to the backend target, it always performs NAT. So by the time the database sees the IP packet, the source IP would be that of the resource gateway in this example. So this is your architecture when your TCP resource lives inside of AWS and your consumer also lives inside of AWS. If we expand this use case, and if we assume that what happens when your database is sitting on your on-prem data center, and you're using a mechanism like Direct Connect to provide IP connectivity between your data center and AWS. So assuming you have provided the resource config and you have associated the resource with resource gateway, nothing actually changes. So if we look at the traffic flow, in this case, against the instance wants to access resource 1, that is onboarded onto VPC Lattice. Traffic gets sent onto the Lattice data plane. Lattice understands this traffic must go to the resource gateway. Now, as long as you have IP connectivity between this resource gateway and your backend target, or which is the TCP resource in this case, Lattice can send that traffic as well. So the pro tip here is when you define your TCP resource, that can either be an IP address or that can be a fully qualified domain name. So in this case, if you provide an IP address of your backend database that's sitting on-prem, this architecture would work. Another thing to keep in mind is, as of today, if you define your resource config with a fully qualified domain name, it must be publicly resolvable. All right, so let's expand this use case even further. Now let's say you have some resources that are already onboarded onto Lattice, but this time your consumer is sitting outside of AWS. The consumer in this case is sitting in an on-prem data center. And again, you're using a mechanism like Direct Connect to provide IP connectivity between data center and AWS. So in this case, your usual VPC association will not work. Why? Because VPC association with service network only provides access to resources that live within that VPC. So this is where you need a different Lattice construct, which is called a service network endpoint. The service network endpoint will consume IP addresses from your edge VPC in this case. And then you would provide an endpoint association, which basically is saying that this endpoint now has access to my Lattice service network and the applications or the services that are onboarded onto the service network. Now, every time you onboard a resource or an application with the endpoint, you get routable IP addresses from within the VPC. Now, a lot of you already know where this is going. You have a routable IP address. You have IP connectivity. So all your consumers need to do is be able to hit or access that routable IP address. Once those consumers start accessing this endpoint or this routable IP address on the specific port, now the traffic again gets sent on the Lattice data plane. Once traffic is on Lattice, Lattice knows where to send that traffic and whether to a service or to a TCP resource. So the pro tip out here is use the service network endpoint association when your consumers are sitting outside of AWS. Why? Because this will give you the routable IP address that your consumers can hit. So now let's talk about how VPC Lattice would coexist with your traditional networking deployment, for example, with Cloud WAN or Transit Gateway with an inspection firewall. So let's say this is the architecture that you deploy for your pilot or for your POC with VPC Lattice. And in addition to this, you also have an existing Transit Gateway or Cloud WAN deployment going on. Your Transit Gateway or Cloud WAN has attachments into the same VPCs. And you also have an inspection VPC connected to Transit Gateway or Cloud WAN. So the good news here is that the laws of VPC routing still apply. So inside of these app VPCs, if let's say you have a default route pointing to Transit Gateway or Cloud WAN, that route will still be used. The only situation in this scenario when Lattice is used is when instances in app VPC 2 are trying to access the EKS cluster in app VPC 1. For everything else, you can continue using Transit Gateway or Cloud WAN. So the major point to take away from this slide is that let's say you have an existing Cloud WAN or Transit Gateway deployment and Lattice starts appealing to you, you can spin a pilot or a POC within the same network as well, as in they can all coexist together. So now let's compare the two models. On the left-hand side, we have Cloud WAN Transit Gateway and a network firewall. And on the right-hand side, we have Amazon VPC Lattice. The first point to keep in mind is with Cloud WAN or Transit Gateway, that's a network-to-network connectivity. And because of that, you cannot have IP overlaps. Whereas with VPC Lattice, since you onboard specific applications and provide access to only specific consumers, you can work with IP overlaps as well. Actually, as a matter of fact, your consumers and your producers can be on different IP versions even. Your consumer can be IPv4, your producer can be IPv6, and vice versa. So the IP version or overlap doesn't matter in the world of VPC Lattice. Secondly, for auditing or visibility, you can use VPC flow logs or transit gateway flow logs on the left side. With Lattice, you can do that with VPC Lattice access logs that gives you rich layer 3, layer 4, and layer 7 information as well. And in addition to that, since you onboard your specific applications onto Lattice, it becomes very easy for you to discover a list of all applications that exist in your network. So it goes beyond traditional IP addresses and CIDRs. Now, this is interesting. When it comes to data processing charges, in the Cloud WAN or Transit Gateway-based model, the data processing charges will apply for Cloud WAN and Transit Gateway, or Cloud WAN or Transit Gateway, and your network firewall, and also your elastic load balancers. For example, any application load balancers that you may be using to natively expose your service. On the Lattice side, data processing charges are on Lattice only. So the major thing to keep in mind is, since Lattice also acts as a load balancer, you can natively expose your applications onto VPC Lattice. So there may be some cost savings out there because it allows you to retire one level of your load balancers. Then finally, this comes up often. For a multi-region scenario, Cloud WAN supports that out of the box with dynamic routing. With Transit Gateway, you can do Transit Gateway peering and static routes. Now, VPC Lattice, as of today, is a regional construct. So if you have a scenario where your consumers and your producers are in different AWS regions, you first need to provide IP connectivity, the underlay IP connectivity across the different regions using mechanisms like Cloud WAN, Transit Gateway, or VPC peering. Now, once you have the underlying IP connectivity, once routing is working, all you need is a routable endpoint. Now, how do you get a routable endpoint with VPC Lattice? That's where the service network endpoint comes into the picture that we spoke about earlier. So net-net, multi-region with VPC Lattice can also work, just that you need to stitch the underlying IP connectivity separately. All right. All right, so with this, folks, we are going to move into the human to workload traffic pattern. So this is the remote workforce connectivity. Now, this is the diagram you saw earlier. Your use case is you got a remote access user on the bottom right trying to access some AWS applications on the left side. And in this case, we are going to be talking about AWS client VPN first. So it is basically a client-based client VPN service. Your client can be an OpenVPN client, or you can use an AWS client. From an authentication perspective, you can use various mechanisms like Active Directory or SAML, or use certificates for mutual authentication. Now, on the authorization side of the house, with Client VPN, you get a Client VPN endpoint, and you can apply security groups over there. Additionally, you can provide network-based authorization by using authorization rules on the Client VPN. What that basically says is, for some contextual information about a resource, about a user that my SAML-based identity provider provides, give access only to specific networks. So again, network-based authorization. The pro tip here is your client VPN-based deployment would work well with your traditional firewalling architectures. Why? Because the client VPN gives you a VPN endpoint inside of a VPC. You can attach that VPC with your Cloud WAN or Transit Gateway. Once you have that attachment, you can use routes and routing tables to punt traffic through a firewall. So for the same requirement again, let's look at an alternative with Amazon Verified Access. So your use case remains the same. You have a remote user on the right side. trying to access some AWS workloads or applications on the left side. So AVA, or Amazon Verified Access, allows your remote users to access workloads deployed in AWS without using a VPN. For this, all the user requests first hit the AVA instance or verified access instance. How do you do that? You onboard individual applications onto AVA. When you onboard your applications, you get an FQDN. Now, when your users try to hit that domain name, that's how you attract traffic into AVA. Now, AVA integrates out of the box with IDPs or identity providers and optionally enterprise device managers as well. So when a user request hits verified access, it first goes to an IDP to see if the user is authenticated or not. That part is mandatory. The IDP can send some contextual information about the user as well. For example, is the user's email ID verified or not? Optionally, you can integrate with an enterprise device manager as well to keep an eye on the device posture. Now with AVA, every user request is evaluated in real time, and it works with both HTTP, HTTPS, and non-web apps as well. For web apps, it's a best practice to associate WAF with your AVA instance so that you can provide firewalling or protection for the web apps that web application firewall provides. Now finally, you can apply fine-grained policies on the applications that you onboard to AVA, and after the IDP authenticates all the user requests, and after your AVA policy says the request is good, only after that AVA sends traffic to the backend application. So from this perspective, it provides an alternative to a firewalling architecture. Now we spoke about policies, so let's dive into an AVA policy and see what it looks like. So first we define the structure. You have to provide an effect, which is permit the request or forbid or deny the request. Then optionally, you can provide specific value for principal, action, and resource. And then there is a condition clause, wherein you can provide match statements on the contextual information about the user. Pro tip here is forbid always takes precedence over permit. Now here's a sample IP-based policy. We're going to start super simple. So here I'm saying permit the user request if the user's IP address is in a specific IP address, is a specific value or a specific range. Now you would use this only if you know that certain clients will deterministically always have an IP address. Let's look at a slightly more involved policy now. So in this case, I'm saying allow the request only if the user is part of a specific identity provider group. For example, the user might be a part of an HR group or a finance group defined within the identity provider. Additionally, allow the request only if the user's email ID is verified. And on top of that, also ensure that the user's Jamf risk profile is low. So the net takeaway here is you can use operators like and or to create really advanced and involved statements. Now, AVA allows you to create and attach these policies on a per application basis, but as the number of your applications grow on AVA, it might become a little cumbersome to manage all those policies. So for that, the best practice is to club your applications that require similar connectivity and security policies into an AVA group, and then apply these policies on the group directly. So now let's see if verified access can coexist, or how it can coexist with your Cloud WAN or transit gateway based deployment. So in this case, let's say AVA starts fitting your requirements and you want to cut a POC or a pilot. This is where you start, where a set of remote users are using AVA to access an AWS app. Additionally, you have your Cloud WAN or transit gateway based deployment that has attachment into your inspection VPC and into your application VPC as well. Now, if let's say you have a set of existing users that are using client VPN, that where the client VPN VPC attaches into the Cloud WAN or transit gateway, that part can continue to coexist with your AVA deployment as well. So again, AVA can coexist with your transit gateway or Cloud WAN based deployment. Let's again compare the two models. On the left-hand side, we have the traditional model with transit gateway, Cloud WAN, client VPN, and firewalls. On the right-hand side, we have AVA. So firstly, again, with transit gateway or Cloud WAN, you provide access to specific networks or CIDRs. Whereas with Ava, you onboard specific applications and you provide access only to those applications. Then the second point is re-authentication. So on the left side with client VPN, you can use maximum session duration to say that your client should reconnect, for example, after 8 hours or after 12 hours. Whereas with verified access, since every request is evaluated in real time, there is no concept of a reconnect. Then this is interesting. So with Transit Gateway or Cloud WAN and client VPN-based architecture, you can create slightly advanced architectures. For example, bringing in your remote users' traffic into a client VPN VPC, and then using Transit Gateway or Cloud WAN, sending that traffic to, let's say, a centralized egress inspection VPC for creating internet egress use cases. Whereas with Ava, you provide secure access only to AWS workloads. All right. So folks, with this, I'm going to summarize the entire section. So earlier you heard Tom talk about internet-based use cases, wherein your users sit on the internet and then they're trying to access workloads within AWS. So the verdict over there is use WAF for your web applications to provide protection. Then use AWS managed services like Session Manager if you have use cases like secure CLI access that eliminate the need for opening specific internet ingress ports. Because in this case, your instances would actually open up an external session to the managed service. And then for everything else, you have your firewalls that you can use to provide protection. For internet egress, the use case is traffic originates inside of a VPC and the traffic is going out to the internet. So for this, the verdict is use endpoints as much as possible. You can apply policies on the endpoints as well. And then in our experience working with customers, using inline inspection firewalls for egress is actually a solid use case. Then we spoke about workload-to-workload traffic inspection. So for this, two of your workloads are talking to each other. I'm showing VPCs, but we saw that with VPC lattice, your workloads or consumers can be outside AWS as well. So for this, the verdict is consider using VPC lattice for your HTTP, HTTPS, TLS pass-through, and TCP applications. And if you have UDP applications, that's where you can continue using firewalls. And then finally, for remote workforce connectivity or human-to-workload, wherein you have your remote users trying to access AWS resources, the verdict here is use Amazon Verified Access that allows you to talk to your web and non-web apps as well. So folks, with this extremely Egyptian hieroglyphic style slide, we are going to wrap up. We are actually doing great on time. So in case you have any questions, Tom and I will be around and happy to answer any of your questions. Please complete the session survey in the app as well, because that tells us if we should continue running such sessions. Thanks, everyone.